minute, so just grab it. Okay, so hello everyone. Thank you so much for coming. Just as a reminder, there's a CfA-wide meeting starting at 1:30. So today we have a sort of a tight schedule. And today we're having two speakers. So our first speaker is Amruth Alfred. And he's originally from the island of Sri Lanka, and he's a URC postdoctoral fellow at the University of Hong Kong. Amruth is the recipient of the 2023 Hong Kong Young Scientist Award, which is given annually to the best PhD research in Hong Kong within physics, chemistry, and mathematics, along with the 2023 IAU PhD Prize Honorable Mention, which is given to the most remarkable PhD thesis of the year. His research focuses on uncovering the nature of dark matter, a mysterious substance that comprises a staggering 25% of the mass of the universe and is predicted by Einstein's theory of general relativity. By providing a credible explanation for resolving the 2 decade strong lensing anomaly problem that has plagued the community, Amruth's research has provided a new avenue to test the potential of ultralight particles to compose dark matter, as opposed to ultramassive particles. This work was featured on the front cover of the June 2023 issue of the Nature Astronomy magazine, and this has been, scientific journal, and this has been rated as within the top 1% amongst all research articles across the journals for online attention. So today Amruth will be introducing his work, and the title of his talk is Revealing Dark Matter under the Gravitational Lens. So please, Amruth, take it away, and thank you very much for accepting our invitation.
So can you guys hear me well?
Yes.
Okay.
Yes,
perfect.
we can.
Okay. Hey guys, my name is Amruth, and I am a postdoc at HKU. And thank you, Julia, for such a kind introduction. And I would really like to thank Julia for providing me this opportunity to give a talk to you guys here at the CfA. And today I'll just tell you a little bit about the research that I've been doing. I started doing this when I started my MPhil at HKU. And if you feel sleepy or you decide to fall asleep in my talk, you can go ahead and find the work at the front cover of Nature Astronomy on the June 2023 issue. Nature also wrote a news and views about our work, and there were also one of the co-authors is actually Razi, so she's a postdoc at the CfA, so she worked with us when we wrote this paper. And there's really a lot of press releases that were written based off this work, so some of them are really well written. So if you'd like to take a look at these, please reach out to me. I can send it over to you guys. So before I get on to the science, I just wanted to tell you a little bit about my history, where I'm from. So I'm originally from Sri Lanka. It's a small tropical island in the Indian Ocean. And I really grew up in a very rural place. So this is actually a picture that I took just next to the road. And you can actually see 3 peacocks here and 3 peacocks here. So 6 peacocks in one frame. And this is actually quite a normal sight in Sri Lanka. You don't have to go to a park or anything like that. So my town was actually in the mountains of Sri Lanka. It's a town called Kandy, and the weather is very pleasant here throughout the whole year. So Sri Lanka doesn't really have seasons. It's rain or no rain, and I didn't really own any winter clothes. So it's really just pleasant weather all year around. And aside from my scientific career, I actually used to be a professional gamer. So I played video games for a living, or my parents wouldn't let me do it. Yeah, this always gets the most interest when I give talks. All the students love hearing this. So this is me actually at the Asian Games, which is essentially the Olympics, but for all of Asia. So in 2018, they decided to have video games as one of the medal events. So you could actually win a medal for this. And I participated there in 2018. So I came to Hong Kong after high school for my undergraduate degree at HKU. So I've actually been here a very long time, almost 11 years. And this is a picture I took from the top of the physics building where the telescope dome is. And all the buildings that you see on the left here, and also the middle, they're all part of the university. So they're all different faculties and departments. And the mountain that you see here on the left is called the Peak. So this is the tallest mountain in Hong Kong Island. And a lot of students, and us included, we regularly hike up when the weather is pleasant. So it's a really nice place here. And this is just a small part of our research group, just about half of the people in the group. We have a wide range of students, from high school students who come to do research in the summer that I help mentor, to undergrads, masters, PhD students. So it's really a nice environment we have here. So that's hopefully enough about me. Move on to the actual science. So the story of dark matter really began in the 1930s with Fritz Zwicky. Now, Zwicky was an incredible person with a lot of creative ideas. And one of his research projects was to look at the velocities, or the speeds of galaxies in galaxy clusters. Now, he was looking at the Coma cluster, but this is a picture of a different galaxy cluster. But what he found was that to explain the speeds of these galaxies, you need a lot more mass than can be seen in the visible wavelength. So he naturally called this dark matter. Now, Zwicky was a hard person to work with. He was very famous for having very humorous insults to people he didn't like. One of them was he would call people spherical bastards because no matter how you looked at them, they were still bastards because of spherical symmetry. So Zwicky was hard to work with. He didn't have a lot of friends, and so people didn't really listen to him. So for almost 40 years, until the 1970s, this sort of went ignored. And then in the 1970s, when astronomers like Vera Rubin, for example, started looking at the speeds of stars orbiting galaxies, so individual galaxies now, they looked at the rotation curves, and they again found that you need a lot of mass to really explain the speeds of these stars and the rotation curves. Today, we know that dark matter takes up of about 85% of the mass in the universe, and it's really considered one of the really urgent questions in all of physics, not just astronomy. The reason for this is the standard model, which is one of the pillars of modern physics, the other one being relativity, doesn't predict a candidate for dark matter, right? And so dark matter is the clearest signature, amongst others, that the standard model is incomplete. So naturally, people proposed extensions to the standard model, and so it predicts a large range of particles. And the leading candidate for a long time now has been the WIMP, so weakly interacting massive particles, right? All you need to know is that these are massive particles, maybe about 200 times the mass of a single proton. So I've taken a cutout here from Nature, it says last chance for WIMPs, because despite decades of searches and billions of dollars of funding, laboratory experiments really haven't detected any sign of a particle. And it's really thought that the coming decade is the period of final reckoning to detect these WIMP particles. So some people don't want to wait, and there are alternative candidates, right, for dark matter. A serious contender is the ultralight particles. So these particles are very light in mass. One of the candidates is the axion. Now, the axion, if you haven't heard of it before, it was a particle originally proposed by Frank Wilczek, who won the Nobel Prize in 2004. He proposed this particle for a completely different reason, to solve the strong CP problem in physics. And if you're thinking, this is some kind of fancy scientific term, it's not. So Frank Wilczek, he said he was in his kitchen and he saw this detergent lying around. And because this particle cleaned up a problem in physics, he decided to name it after the detergent. So that the detergent actually came first. Now, I don't know how common this is in the US, but in Hong Kong, you can find this at every supermarket, this brand. And recently I saw that they don't only sell Axion, they actually sell Ultra Axion. So someone in the detergent business is keeping up with modern physics, I guess. So that's how the name came to be. So now if you're wondering what cosmological simulations predict for these types of dark matter particles, I'll tell you very quickly. The reason cold massive dark matter particles have been the popular candidate is because they reproduce the large-scale cosmic structure, right? It matches very well with observations. Problem is, over time, there have been other problems. One of them is the missing satellite problem, where simulations vastly over-predict the number of satellite galaxies, and also the cusp core problem, where simulations predict very steep density profiles for the insides of dwarf galaxies, whereas we infer cores from observations. So this is some of the current considered problems with massive particle dark matter. On the other hand, for ultralight particles, the first simulations were only done in 2014 because they are computationally very expensive, right? As you can see here, the first simulations were featured on the cover of Nature Physics, and this is really showing you two dark matter halos that are merging, and you can see that there's a lot of the structure surrounding the dark matter halos. The reason this is happening is because ultralight particles, because they're light, their wave behavior is highly pronounced. If you recall the wave-particle duality and the de Broglie wavelength equation, the wavelength of a particle is inversely proportional to its mass. So because these are so light, their wave behavior is much more pronounced, right? And the reason you see these patterns, so these interference patterns between the ultralight particles, the overdense regions are due to constructive interference, the underdense regions are due to destructive interference. So on the large scales, ultralight particles and massive particles are actually the same, and they have to be to agree with observations. But due to the uncertainty principle, there's a suppression of low mass dark matter halos in ultralight particles, and you can see how this would naturally alleviate the missing satellite problem. Now, if you zoom in, right, to the galactic scales or subgalactic scales, then really interesting things start to happen. First, the simulations predict that there's this core-like structure at the center of every dark matter halo. So it's a sort of shallow, flat density profile. And again, you can see how this would potentially solve the core cusp problem. And more interestingly, there's this pervasive density modulation. So throughout the entire dark matter halo, you have these very powerful density fluctuations in mass, right? As you can see here in this picture. So in my PhD, the question I asked was, can we detect signatures of these density modulations? And can we detect these signatures in gravitational lensing? So I'm sure a lot of you, or all of you, are familiar with gravitational lensing, but I've put in a very single slide just to explain what it is. If you have a distant galaxy here, let's say this white blob, and along the way the light takes to reach us, if there's an intervening galaxy, Einstein's theory of general relativity tells us that the light gets bent, right, due to the mass. What you see in projection with your telescope is actually a configuration like this, where you see these 4 point sources, which are typically called multiply lensed images, and you also see the lensing galaxy in the middle, right? So you can also probably see this faint ring-like structure here, typically called an Einstein ring. And these images and the ring form around what's called a critical curve region, right? So this is just a technical term for telling you that these regions are high magnification, which means the light is really amplified a lot in these regions, which is why you see lensed images there in the first place. So if I was to do the same now to compare between massive and ultralight particles, this is how I would do it, right? So this is how we do the test. So first, I'm showing you a panel here, which represents the surface mass density of a galaxy, right? A single dark matter halo, if dark matter is comprised of massive particles. Now I zoom into a small region, which is why you see here, if you go towards the center, the density increases, right? And as you go outwards, it decreases. Now, if I was to calculate these high magnification regions, right, the critical curve, this is how it would look like. So you would expect lensed images to form near these regions. So now it doesn't look weird. It looks like a very smooth curve, and that's what we expect. Now for ultralight dark matter, because I've shown you how it has all these density fluctuations, you can already hopefully see that the density distribution doesn't look smooth, right? You see all these ripples and features. Now, what's interesting is if I plot the critical curves, the high magnification regions, you can see that things aren't smooth anymore. Things are chaotic. They have this wavy pattern, and all sorts of islands of magnification start forming. Now, if you wanted to understand why this is happening, I'm going to subtract away the global component of dark matter, and I'm just leaving behind the density fluctuations that are predicted. So you can see here the red regions are overdense and the blue are underdense. And if I plotted the contours of these high magnification regions, you can see that they trace the underdense and overdense regions. So they trace and they form these high magnification regions. So in lensing, in observations, you don't actually see critical curves or you don't see high magnification regions. What you see are lensed images. So here I'm going to show you what we expect to see when you have massive particle dark matter. This is a typical lensed image configuration, these 3 white arclets, right? And I've marked their centers with a red dot for reference. So they form a very symmetric pattern. If I was to look at ultralight dark matter, you'll see that the images have now been perturbed in position. As you can see, there's a difference between the red dot and the white arcs. They've been pushed apart by the density modulations. If you have a sharp eye, you'll also notice that the arcs have changed in size. And in lensing, size means magnification. Magnifications mean brightness. So what you've just seen is that the density fluctuations are capable of perturbing both the positions and the brightnesses of lensed images, right? Now, to really drill this into your head and help you visualize why this is the case, right? I've made this visualization where you can see on the left is what you expect for massive particle dark matter. You have this galaxy in the middle, it's bending space, and light from a distant galaxy gets bent. And you have these 2 lensed images. The image on the right is bigger and therefore brighter. Now, if dark matter was made of ultralight particles, there will be these density fluctuations, and therefore the light will take a much more winding path through the space-time. And potentially, what could happen is that the image on the left now becomes brighter due to the small variations caused by the density fluctuations. So hopefully this visualization lets you understand why the lensed images are capable of being perturbed in their properties. Now, this is where I tell you that historically, for almost 2 decades now, there has been a problem in lensing called the lensing anomaly problem. What this is when astronomers make models for lensed systems, they find that they actually can't reproduce the brightnesses of the lensed images in a lot of cases. So this is not a rarity. In most cases, there are significant discrepancies between model prediction and observation for the brightnesses. Now, a lot of studies find this, more and more studies find this, even this recent study in 2020 by Nirenberg et al. And naturally, the first thing people said was, well, what about the substructures predicted by standard WIMP dark matter, right? These subhalos, can they resolve these anomalies? And time again, studies have found that it's very unlikely that these are the whole reason for anomalies. So they're unable to resolve the anomalies. More recently, with very high resolution observations with VLBI, so very long baseline interferometry in the radio, so these are sub-milli-arcsecond precision, people find that not only can they not reproduce the brightnesses of lensed images, they also can't reproduce the positions. So we can't reproduce anything we see, right? You only see positions and brightnesses in lensing observations. There's no other variable that you typically see. So we can't reproduce anything. So this has been a problem that has really plagued the field for a long time. So in our work, we asked, well, can ultralight dark matter and these unique properties potentially resolve these anomalies? So to do this kind of statistical test, first, we need to remember, I need to tell you that ultralight dark matter, these interference patterns, they're random in nature, right? The interference is random. So you can't simply make one realization, you need to make many. And in each realization will produce a different set of positions and brightnesses for the same system for lensed images. So to really do our tests, we have to make a bunch of realizations. And here, I'm going to now show you what kind of position anomalies you expect due to ultralight dark matter. So in the gray histogram, I'm showing you what we typically see in observations, the positional disagreements, right? What we call the anomaly. Typically, VLBI observations find a disagreement of a few tens of milliarc seconds. Now, the dashed line here, the dashed curve here, is the best fit prediction from ultralight dark matter. So I'm showing you the prediction for one particular mass of the axion, which corresponds to one particular wavelength. I've done many others, and I can show them to you in the Q&A if you want to see. But here I'm showing you the best fit. And again, we do the same for the brightness. So the brightness anomaly is just a measure of how discrepant are the brightnesses. Again, you can see that there's a general agreement, a statistical trend of agreement between the ultralight dark matter predictions as well as what's observed. Now, if this doesn't make you happy, and it probably shouldn't because it's just a general test, what we do is we look at a specific system, right? We look at one of these VLBI systems, which has a structure like what I show here on the top right. There's an optical core in the middle, and it's straddled by two radio jets. Now, this thing was lensed, and it's been quadruply lensed into 4 sets of lensed images. This is one of the systems that exhibits all these anomalies. And we now make lens models to test whether we can reproduce these anomalies. So here, in the ellipses are the observed positions of these lensed images. The sizes correspond to the measurement uncertainties. The crosses are the best fit WIMP model predictions. And I don't know if you can really see the dots. Maybe it's too small on your screen, but this is the result for one realization of ultralight dark matter. So you can see it's kind of in poor agreement for 2 of these images. The dots fall outside the ellipses. Now, obviously, I do this for a bunch of realizations to capture the randomness of the density fluctuations. And eventually, you'll find that there are always realizations that can successfully reproduce the positions of the lensed images. Now, this is just one of the many tests that we do, but in the interest of time, I only can show you this one. So, incredibly, very surprisingly, with no fine-tuning really, I hope someone asks me this in the Q&A, with no fine-tuning really, the ultralight dark matter model is really able to surpass a lot of stringent tests that we put every lens model through. So in conclusion, this was really one of the first times where anyone has tested ultralight dark matter in this aspect. And it's just very lucky or serendipitous that we solved the lensing anomalies. That was not the original goal of the project, right? And now there are other astronomical observations which also find independent evidence for the same axion mass that we find as the best fit. And with all the data that's coming in from all sorts of telescopes, HST, JWST, we're really starting to be able to do a lot more tests on the nature of dark matter. One of them is using lensed supernovae, type 1a supernovae in particular. They all exhibit very severe lensing anomalies, which is very interesting. And we've really started to understand the importance of multi-wavelength observations. Now, the VLBI observations, which I showed you in radio, but also in X-ray. There are not many lensed quasars that have been observed in the X-ray. These would serve as an additional set of constraints to test any lens model. There are also anomalies in the arrival times of the signals. Now, in optical, the precision for time delays is very, very poor. So we're not able to really use this to constrain lens models. But I know that the precision can be high in other wavebands, in radio, for example, or even in X-ray. So this is potentially one way to use multi-wavelength observations to shine new light, a new way to test this kind of dark matter. The final one is, I think, would be most interesting to you guys, especially if you're working in X-ray or gamma. Now, these are lensing events in a galaxy cluster. Each circle here corresponds to a lensed event. And these are the recent transient events that have been detected by HST and JWST. Now, it's a very hot topic. It's very recent, and their origin is unknown, right? People think one of the leading explanations is that these are microlensing events. So they have been temporarily brightened. They brighten in one epoch and they disappear. But we don't really understand their origin, right? And most people who work in lensing, they really look only in the optical. So I think it would be very interesting if there were X-ray observations or gamma ray observations of these lensed arcs and galaxy clusters to see if there are counterparts to these optical transient events, because that would really be extremely interesting in understanding the origin of these events. So I was hoping to actually hear about this from hopefully someone says something in the Q&A. But hopefully I've convinced you that doing all these tests and doing very stringent tests with all these observations will really tilt the balance between massive particles and ultralight particles, hopefully pointing the path towards new physics. So with that, I'll end my talk. Thank you very much.
Thank you very much, Amruth. Any questions for Amruth from the room or from Zoom? Or any comments regarding the X-ray or gamma ray photo walk?
Can you hear me? Can you hear me?
Yeah. Yes. Yeah.
I have two questions. One is, you show some order of 10 to 100 parsec perturbations in the critical curves. How do you know they're coming from the dark matter, right? They could be baryonic as well. How can you justify this? Second, there are other experiments like structure formation, superradiance. There are at least 10 other experiments showing that the ultralight particles could only be a fraction of the dark matter, but not the whole thing, right? Because otherwise you should suppress every structure formation beyond megaparsec scale, right? Like for these guys. I'm wondering, are you claiming a fraction of it or just the totality of the dark matter? Because it's also important. I mean, even if it's a fraction, it's a huge deal. It has huge implications. But I think the totality of the dark matter in terms of ultralight particles has been ruled out 5 years ago, whatever. Yeah, I'll be happy to hear your comments.
Okay, thank you very much for those questions. So the first one is about why we have these parsec scale critical curve fluctuations. So the reason this is primarily from the dark matter is because in the simulations you can see that the dark matter particles, the reason they form these patterns is due to the quantum interference between them. So they follow this characteristic de Broglie wavelength where you get fluctuations with that exact same scale. Now, with the addition of baryons, which we've tried with baryonic profiles, what happens is that these fluctuations get dampened in amplitude. So their amplitude is reduced relative to how much baryons you have, because the typical baryonic profiles tend to just smoothen out the fluctuations. So at least from these simulations of dark matter, of ultralight dark matter, the fluctuations, such very corrugated density fluctuations to the critical curve, are only capable with the dark matter interference pattern. If you were to have structures, baryonic structures, or individual subhalos, dark matter subhalos, you wouldn't have this kind of systematic fluctuation to the critical curve. So that's the first question. The second question is, there are a lot of studies that have been done to place constraints on dark matter. Now, when we do these lensing simulations, people don't consider fractions of dark matter. It's just generally considered a large fraction of the dark matter is comprising the lensing galaxy, so it's not sensitive enough to test different fractions of dark matter. And the constraints that have been placed on the axion mass, it spans a wide range in magnitude. Now, to get this paper out, we had to discuss very strongly why the mass range that we choose is not ruled out, right? Or the paper wouldn't get accepted. This was one of the comments by the referees and the editor. So we had to really show some of these studies, they place constraints, but these constraints are not strong enough to entirely rule out that mass range. And the mass range that we actually get from these lensing studies is in the range that isn't ruled out by a bunch of observations. There are some constraints on the fractions of dark matter, but a large fraction of the dark matter still can be in the form of ultralight dark matter for the mass range that we're probing. Now you need to remember that the mass range spans orders of magnitudes. So the specific range we use here is 10 to the minus 22 electron volts. And So that mass range doesn't have significant constraints like from other observations, but it's obviously still a hot topic under research. So if you're interested in more of the references, I can discuss with you later. But thank you for those questions.
I'm afraid we need to move on, but Jason has a question also on the mass or the ultralight axion mass, and it's in the chat. But yeah, thank you very much, Amruth. And just as a reminder, Amruth has joined us from Hong Kong. He's very late there. So if you have any further questions for him, please feel free to sign up or contact him using the spreadsheet, and the email is in there. So let's thank Amruth again, and good night.
Oh, thank you so much, Julia, and thank you everyone for listening. And please don't hesitate to reach out to me to ask questions. So thank you very much.
He's from Florence. That's pretty much defines him, really. And he got his PhD in 2002 with Marco Salvati, and then has worked at Archetri for 13 years after that, before moving to the University of Florence in 2025. I've checked ADS, we've written 57 papers together, amazing, of which, it's about a good measure of his productivity. You can tell that because 16 of them are Risaliti et al, and 2 of them are Alfred et al. But we did a lot of things on eclipses, on AGN, cometary eclipses, black hole spin, winds, new star. He convinced me the broad iron K was real. But I think the most important thing is we did we helped Monica Young do her thesis on alpha OX, and could we tighten up that relationship? And I think that's, you'll see he's gone a long way with that idea since then. So Guido.
Thank you. Maybe I need the.
You need this.
Yeah, okay. Yeah, I can use this. Okay, so thank you. It's a pleasure to be here again after several years. And actually what I'm gonna talk today is a work in progress, indeed. I do not have anything published yet, and I'm here also to discuss with my collaborators who are listed here about the next steps. So what I'm showing you is nothing is finished, and that's also why.
Sorry, Guido, can you share your slides on Zoom?
Oh, yeah. Okay, so sorry. I have to do that first. So, apparently, I'm out. I'm doing this on Zoom. Yeah, I'm no longer. Is it okay now?
Just put it in presentation mode.
Yeah, sure. Yeah, is it already done? Yeah, I just to go to my. Questo qua. Yeah. Yeah. Okay. And so is that okay now? Can you see?
Yeah, everything is fine.
Great. Basically, I would like to start from a very general argument. So let me start with something which is, trivial, and which has been studied in much more detail for many years. But just to set the fundamentals of the problem. So the problem of accretion disks in quasars, accretion disks in general, but in particular in quasars, has not been solved. We know that we have several models, but none of them is able to reproduce everything we see with observations. And on a very general basis, so on very general physical grounds, you expect that efficient disks, efficient in converting accretion power into radiation, should roughly be geometrically thin and emit locally as black holes. Otherwise, they will not be as efficient as needed to explain the luminosity of the most luminous quasars. Okay, and if this is the case, roughly we have this relation between the temperature and the physical parameters of the disk, and in particular, you see in this formula the global parameters of the systems are the black hole mass and the accretion rate. Okay, so let's say that the temperature of a given ring of the disk and at a given distance r from the center is set by two physical parameters. In this parameterization, it's the black hole mass and m dot. Okay, then we can use there are other ways to parameterize this dependence. We can define a Eddington ratio as the ratio between the total disk luminosity and the black hole mass and mass constants. Okay, and well, sometimes we believe that this is a more physical quantity rather than the m dot itself, because the m dot in physical quantities, in solar masses per year, is something which doesn't describe, the accretion level, because it depends how big is the black hole, of course. So this may be sometimes a better indicator to understand the physical conditions in the disk, and the total disk luminosity is roughly proportional to m dot, which means that we can describe the observable quantities in different ways. And for example, if we consider that the disk extends down to the last stable orbit, well, there is another parameter which is the black hole spin, of course, but let's neglect that as a zeroth order approximation. And so we have that the maximum disk temperature depends on either the luminosity of the disk over the square root of the black hole mass or the Eddington ratio over the black hole mass, depending on how we choose to parameterize. So this is pretty obvious. This is written in undergraduate books, okay? But this is a pretty general quantities. Then we know that the specific models, starting from the old Shakura-Sunyaev model to all the most advanced disk models, differ in how the energy transport happens along the disk, and so there are small corrections to this formula. But overall, the main dependencies are these ones, if of course we have a local black body emission by something which is actually a disk, so it's something thin. Okay, and so what happens if we compare these predictions with observations? I'm just here discussing spectroscopy. Okay, so what we can obtain from spectra of these sources. Then there are also important other ways to test the disk model based on variability, on lensing, and etc. So actually, if we try to test these predictions with the available spectra. In particular, I'm referring to the Sloan quasar catalogs, and we are using the latest DR16 quasar catalog, which contains almost 1 million quasars. Well, actually, if I use this parameterization here with the maximum temperature as a function of the disk and the black hole mass, if I put all the quasars of the Sloan survey in a mass luminosity plot, okay, I have the distribution, and the different colors and the dashed lines are regions of different expected maximum temperature. Okay, so the ones on top here are expected to be colder, so the blue and the red are in terms of wavelength, okay? So these ones on top are expected to be colder, while the ones down here are expected to be hotter. And if you put the numbers, and not just the dependencies of the quantities, you can easily see that you expect that while the green and blue objects in this plot have an expected maximum temperature which is beyond the Lyman limit, so it's not observable in general. The orange and red ones have a predicted maximum temperature which is in the range which should be observable in the zone quasars, okay, because they are below the Lyman break, and so if you go to a redshift of 2 or higher, you should see the maximum of the disk emission and then a decrease of its emission. Do we see that? No, we don't. If we stack the spectra of the Sloan in selected this way, we find a very remarkable similarity. All the stacks are the same. We do not see this expected peak, and we do not see the ones which should be the cold quasars. Okay, and this is something that we have done here, but there are several papers in the past couple of years on the same thing by the group of Chris Dunn, and there is also a Nature Astronomy paper of the past year referring to a universal quasar SCP, referring to this, to this observed similarity. And so, well, I skip this to go straight to the point. I mean, we have a possible solution of this discrepancy, which actually goes in the direction of simplifying the model instead of adding more complication. And I'm just starting to tell you what it is, and then I will show you how it fixes several problems in this field. So basically, what you see on the left is the distribution, the observed distribution of eddy interpolations in log units in the Sloan quasar sample. And you see that the width of the distribution is about 0.45-ish, between 0.4 and 0.45. Actually, this number is surprisingly low, is small. Why? Because all these measurements are based on our estimate of the black hole mass, which is a single epoch virial mass. And the calibration of the black hole mass based on reverberation mapping, or when available the dynamical mass measurements, is based on the papers that everybody uses to calibrate the virial masses. They are of the order of 0.4, 0.5 decks. Okay, and so basically you expect that there is such a dispersion between 0.4 and 0.5 just because of the uncertainty in the value of the black hole mass. And since the editor ratio is the luminosity, which we may think we can estimate, not as bad as 0.4 decks at least, quite precisely. Then we had that this 0.4, 0.5 decks dispersion in the mass should all be in this distribution. And so, where is the room for the intrinsic distribution of eddy interpolations? Okay, so at least from this data, it is possible, and this is what is shown in the right in the right hand side of this slide. It is possible to reproduce this kind of distribution by assuming a universal constant eddy ratio. Well, I assume it to be exactly one value just for to simplify things. One can think about this a narrow distribution, say 1.1 decks in width, Okay, and then if we assume that the true Eddington ratio is roughly the same for all quasars, say about 0.1, or also -1 in log units, which is about the average on the observed distribution. Well, actually, we can reproduce what we observe in the Sloan survey, just allowing for the dispersion due to the uncertainty in the black hole mass measurement. And this is what is done here. Basically, we assume that the Eddington ratio, the true one, is this green value here. And then if we simulate the dispersion due to the black hole mass, basically we end up, well, by construction with the same luminosity distribution. This is by construct, but also with a similar mass distribution, and there is no need for an extra dispersion. So, can we test this hypothesis? Yes, we can. And actually, this is my main point, maybe. And so here, what you see here is a plot. It's a density plot. So this is made of about 500,000 quasars. And so what you see in this plot are two, you see it's a wavelength versus wavelength plot. And in the x-axis, you see the maximum, the wavelength where you expect the peak of the accretion disk based on the virial black hole mass. So the mass estimated with a virial method. Instead, on the y-axis, we have the same. So the peak wavelength for the accretion disk emission, but estimated based on this assumption of constant universal, let's say, Eddington ratio. So when we say, and the green and purple and magenta lines are more or less the value around 1700. That is the minimum value that we need to be sensitive to this peak in the SDSS spectra. I mean, if we have the spectrum peaks at shorter wavelengths, we are not able through the spectral analysis to see this peak. Okay, so if we select the objects that, according to the virial mass estimate, should be too cold, I mean cold enough to be seen in the spectra, and we stack the spectra, we do not see that. So the green spectrum is the stacked one, and while the dashed line is the expectation based on the accretion disk model with the virial mass, and you see it predicts a peak which we do not see. Instead, the continuous black line is the one obtained assuming our with our assumption of universal Eddington ratio. And so this was somehow already known. I mean, the fact that the dashed line is in disagreement with the observed spectra is what I already mentioned. It's been published in several papers already. But the news is that when we do the same with this other group, which is the one which should be the one consisting of the cold quasars according to our prediction, well, in this case, we do see the cold spectra. So the cold spectra exist. We were not looking for them in the right place. Okay, and you see that now our continuous black line fits the data. This is not a fit. This is just superimposing the expectation from the disk model, while the dashed line based on virial masses fails. So I think this is a very direct way to see that there must be something true in this story. And on my knowledge, this is the first time when we see these spectra with this shape significantly different from the standard one. And you see they are few. I mean, this is a density plot, but there are a few hundred out of 500,000. Okay, so if you don't look for them in the right way, even if you have some of them in your stacks, they are diluted in a much larger population of normal spectra, and so you do not see them. So let me just, so last 5 minutes, I would like to show you another test that we did, which suggests that we are on the right track. So another relevant piece of observational information that we have from quasars is the so-called Baldwin effect, so the relation between the emission line luminosities and the luminosity of the continuum. Okay, and this is a non-linear relation because there's, in log units the slope is not one, and in particular, more luminous objects tend to have emission lines which have a lower equivalent width. So they are fainter, let's say. And here you see just examples of what we did. So on the left you have just a zoom of two of these feeds, line versus continuum, and here on the right you have just a list of more of them because we did this analysis in small redshift beams. So just to avoid problems related to the cosmological model that we use to estimate the luminosity. So and also to check for possible redshift evolution of this effect. And so we did this for the main emission lines, so magnesium 2, carbon 3, carbon 4, and the hydrogen lines. And we find the following results. Again, here on the left, I'm just showing the results for the two of the main lines, magnesium 2 and carbon 3. And basically here you see, first of all, in the upper part of the plots, you see the slope of this relation as a function of redshift. And so the points, the green points are our observations, while we also show the dashed lines, which are the expectations from the standard disk model. So plain easily with some basic algebra, it's easy to show that based on the thermal model, the luminosity of the line, if the luminosity of the line is a good proxy of the total ionizing luminosity, then we expect more or less that the luminosity of the line depends on that of the continuum with an exponent 0.75, and then there is an additional dependence on the Eddington on the square root of the Eddington ratio. This is very simple to obtain, and if instead of doing analytical approximations, we do the proper calculation numerically, we get slightly different exponents, okay, which is what we have done. And basically what we see is that we find that the slope is in very good agreement with the expectation of the model. So it's again another indication that after all this model works pretty well. However, this is not the most interesting thing in my opinion in this diagram, because if you look at the lower part of the two diagrams, that's the dispersion of the relation. Actually, this dispersion is not good, it's too good. Okay? Why is it too good? Because in this dispersion, we should have a lot of effects. Okay, first, our approximation that the line is a proxy of the total continuum luminosity, which may be a good approximation, but I don't expect it to be perfect. Then there are the inclination effects, which add to the dispersion. Then the model probably is not, it is a very simplified model. And the Eddington ratio. The distribution of Eddington ratio should appear here in this kind of analysis as a dispersion. Okay, different Eddington ratio should just add the dispersion to the relation. Instead, we see a remarkable 0.1 something dex dispersion, and in several cases it's around 0.1. And let's say there is no room for a significant dispersion in the Eddington ratio. So we are again at the same conclusion that there is no room for any significant distribution of Eddington ratios. which reinforces what I said before. And let's say I stop here just saying that we are working on this, and in these days, while here, following a suggestion by Martin previous week, we think that we can further check this using sources which have multiple observations in this long survey, and that are variable. Because those sources, the different observations, will, by definition, will refer to sources with the same mass, because it's always the same source, but having different luminosity, it means that in those few cases, there are very few, there should be some variation in the editor ratio, and so we could check what happens when it's the editor ratio varying while the mass remains constant, while in almost all the cases, it's the other way out. The editor ratio is about the same, and the mass is what is varying. And I'm stopped here. Thank you very much.
We're out here very soon, but if there's one quick question for Guido. Tony?
Is
When-
this going to be even better with Euclid data?
Yes, I mean, I think that for what we need, Euclid will, if the spectroscopic part will work, etc., it will be very good to extend this kind of analysis to higher redshifts. For, let's say, redshifts up to 3, 4, I think I'm happy with what we have now. Let's say it's not the main problem yet to extend the quality of the data set. It could be good to extend it in redshift.
Okay, I'm afraid we're gonna have to leave the room because of this one clip, so let's thank Guido again.
Oh, that's gonna be-
I stay here for the whole week anyway, so.
Oh, yeah.
So Guido will stay babysitting for the rest of the week. Thank you very much for coming, and anyone who's not attending the CFA is welcome to join us for coffee in the lounge. Thanks.
I was